In this video, we're going to be talking about how to start up any projectile problem. Now, there are a lot of variations to projectile problems, but the two cases I'm going to present to you will give you a good starting point for just about any problem. So the first thing you want to do, no matter what kind of problem is, because projectiles are two-dimensional, which means they go horizontally and vertically, you want to set up an X and Y column, an X column for everything that's horizontal, and a Y column for everything that's vertical. The reason why you do that is because the horizontal motion has no net force. It's just inertia taking it to the right. So you're only going to use this formula in the blue box for the X side. On the Y side, because there's always the force of gravity acting on it and causing some imbalance in the vertical direction, there will be an acceleration. Everything in the red box will be used in the vertical column. So with that being said, we know for sure that we have an acceleration of negative 9.8 meters per second squared on this side. And if you have something with a horizontal launch, there is no vertical velocity in the beginning, okay? It does have a velocity, so it can be confusing because it looks like there should be a number here, but because there is no velocity directed downwards or upwards, you can say that there is no vertical velocity, but there is a velocity on this side. It is completely horizontal. That's basically the way you're going to start off with any horizontal launch. Now from there, typically what you're going to do is you would get one more number on this side or this side, and then you're going to find time, and then the time could be shifted to either side. So on the left side, if you have two numbers, you can solve for time, such as your delta x and your v. Okay, this only has three variables, so if you have two known variables, you can go ahead and solve for the time on the left side. On the right side, you're going to need three known variables because everything in my red box over here has four variables in each of those equations. Therefore, you'll need three known variables. So you're going to have to get a third number, which might be something like a delta y, some kind of change in height, or a final velocity. And then you're good to go from there. Now for our second one, if you have an angle, the first thing you want to do is break it up into the x and y components. And what you're going to do from there is you're going to set up your x and y columns as usual, as you would with every problem, because of the reasons I mentioned earlier. And then you're going to start off by doing a little bit of trig and get this adjacent side over here with your hypotenuse of 20. So for the x component, we are going to do Vx equals 20 times the cosine of the angle. And then for the y component, you would take 20 times the sine of the angle so that you get this opposite end over here. Okay, so after you do that, you're going to get your Vx and your Vy over here. You don't really have to call it Vx because I'm putting it in the x column, but this would be 17.32 meters per second. Over here, we do have initial velocity. This time it's being projected upward some, and that's at 10 meters per second. Okay, now from there, we still have an acceleration of negative 9.8 meters per second squared. And again, you want to grab some kind of number here or here so that you could possibly use time on either of these sides. So remember, time is the only thing that isn't a vector so that you could use it in either column. Now, if you're coming back to the same level it was launched at, you could say that your final velocity is negative 10 because it'll be the same velocity just directed downwards. So that's safe to do if the object lands back at the same level it was launched. Other than that, you're just going to have to read the problem and find some kind of additional variable, and then you could do some more solving from there. In this video, we're going to be taking a look at an airplane drop problem where a plane is flying at 80 meters per second, 1,000 meters above the ground, and as it drops an object, it's going to follow this curved path where it hits the ground, and we're going to find its landing position based on solving its delta x value. So anytime you're solving a projectile motion 2D problem, we want to set up an x and y column. An x column is anything that's moving horizontally, and the y column is anything that's moving vertically. And the reason we do that is because they are different types of motion. In the y column, the motion is accelerated because there is a force, which is a force of gravity acting vertically. And then in the horizontal direction, it's moving at a constant velocity because there are no forces acting side to side once the object is released, assuming that we're ignoring air resistance. Now, if we take a look at this problem, we're going to go ahead and write down all our known values. Now, a couple of them are posted on the screen, but then a couple of them you'll have to know conceptually. So we have the 80 meters per second, which is clearly a horizontal value. So we're going to put the velocity of 80 meters per second in our x column. And then our 1,000 meters is going to be a vertical value. So our delta y is going to be negative 1,000 because our package is falling 1,000 meters. So its displacement is negative 1,000 meters. Now, a couple other things we can add in this column are the acceleration due to gravity, which is negative 9.8 meters per second squared. And the tricky one that people tend to forget sometimes is the initial velocity of 0 meters per second. And that's because there isn't any vertical velocity moving upwards or downwards when the package is dropped. It's just carrying a horizontal velocity of 80 meters per second because it was riding on the plane. So there is no vertical velocity there. Now, it looks like we have a lot more to work with on the y side, which we definitely do. And then we want to use that information to eventually solve for a delta x on this side. Now, on the left-hand side, we only have one formula we can use, which is delta x over t equals v. And we already have the velocity, so we're already good there. We just need to find the time. And then once we find the time, we could do one step of algebra and then solve for our delta x, our final landing position. So on this side over here, we have our three values. So we're only going to want to use accelerated motion formula. So we will not use this on the right side, only on the left side. So based on the values we have, we are going to use the formula delta y equals VIT plus 1/2 AT squared. And then because of this 0 being plugged in here, we can go ahead and cancel out this first part because it's all going to go to 0 anyways. So let's go ahead and plug in the values we have and then solve for our time. So I got a time of 14.29 seconds. All I did is set the delta y equal to 1/2 AT squared. 1/2 times negative 9.8 is negative 4.9. So I divided both sides by negative 4.9 and took the square root of both sides, which gave me our time of 14.29 seconds, which could be used over here. So we have a delta x value that we're looking for. We have a time of 14.29 seconds, and that equals 80 meters per second. So if I go ahead and cross multiply the 14.29 over to this side, then that gives me our delta x, which equals 1,143.2 meters. And that is our final answer of where our package is going to land. Now, there are variations of this problem, such as being given the delta x and then solving for the speed that the plane is flying, which is the initial velocity of the package in the horizontal direction. In that case, it's not going to be very different than the version I just showed you. The only difference would be you are given the delta x, you would solve for the t on the vertical side, such as I did here with the delta y, the a, and the vi. And then once you have the delta x and the t, you would just divide those two, and then that would give you the velocity, which would be the initial velocity of the package, which is also the initial velocity of the plane. So if you're given that variation, it's going to be a very similar setup and calculation, just one little difference at the very end. I'm going to be doing a full range projectile problem. We're going to be solving for just about every unknown variable that you can for this type of problem. We're going to solve for the total time in the air, the range, which is basically the delta x, the maximum height, which is the delta y at the peak, and then the final overall velocity, which we'll call a VF. Now, our original situation is this. We have a projectile shot from the ground level, and it is fired 30 degrees from the horizontal, and it has an initial velocity of 10 meters per second. So with that information given, we can go ahead and solve for each of these things. So as usual, what we're going to want to do is separate everything into an X and Y column. And just a reminder why we do that is because everything in the X direction is horizontal and it does not have a net force, therefore it's moving at a constant velocity. So anything that's in this column, we will only use this formula right here, the constant velocity formula. Everything in the vertical direction we place in here because it's only directed up and down, and up and down does have a net force because of the force of gravity, so we're going to use all three of these acceleration formulas potentially. Okay, so with that being said, our first step is to take our velocity and break it up into its x and y components because the 10 meters per second, it doesn't fit into a horizontal or vertical column. So we want to find a Vx and then also a Vy as well using this 30-degree angle and then our hypotenuse of 10. So what we're going to want to do is for the Vx, this is the side that's adjacent to the 30-degree angle. So we're going to want to use the adjacent side in combination with the hypotenuse. So we're going to want to use cosine. So the Vx is going to be the 10 meters per second times the cosine of 30 degrees. And then that's going to give us 8.66 meters per second. For our y side, it's opposite the 30-degree angle. So we're going to want to use sine for that one, 10 meters per second times the sine of 30 degrees, and then that's going to give us 5 meters per second. So we can go ahead and place those two into our x and y column. We have a velocity of 8.66 meters per second and an initial velocity of 5 meters per second. On the left side, I didn't have to write a VI or VF because it's a constant velocity. It's not changing, it's 8.66 the entire time. But on the y side, that is my initial value. Now, we know that once it gets projected into the air, it's in free fall. Its acceleration is negative 9.8 meters per second squared. And then we also know when it comes back to ground level, the final velocity is going to be the same as the initial, but because it's going downward, we're going to drop a negative sign in there. So now we're ready to go ahead and solve for our time. And what we're going to do is we're definitely going to use the right column over here because we only have one number to work with over here, so that's not very much. So the formula we're going to want to use is the first one over here because that's the one we have 3 out of the 4 variables and t is our unknown. So let's go ahead and plug into that first one and see what we get for time. So all I had to do was put in our acceleration, -5 minus 5, which is -10 up top, cross multiply these two, so it's basically -10 divided by -9.8, and I have a total time of 1.02. So we can go ahead and check this one off of the list. Now the second thing is we're going to find our range. Now because time is not a vector, it could be slid into our x column, which is what we're going to do. We have our time right over here, and we can make that 1.02 seconds. So we can go ahead and use our constant velocity formula and go ahead and solve for that delta x. All right, now we plugged in everything into this formula. We basically multiplied both sides by 1.802, and then 1.02 times 8.66 is 8.83. So then that takes care of our range. So let's go ahead and clear a little space so we can go ahead and solve for our max height and our final overall velocity. Now for our maximum height, we could do this one of two ways. We know that if our total time in the air is 1.02, then if we take that total time of 1.02 seconds and split it in half, then we would get 0.51 seconds, and that would be the time that it takes to rise or the time it takes to fall. So we can use that to find our maximum height, or we can also use a VF of 0 meters per second, because at the very peak in the y direction, not the x, because the x maintains a constant velocity of 8.66, but in the y direction, it's not rising at that point, so you could use a final velocity of 0. Okay, so you could do this one of two ways. You could use the second formula and then plug in the time of 0.51, or you can use the third formula, and then you can take advantage of using that VF of 0. It doesn't really matter which one you use. I'm just going to go ahead and use that second one and see what we get for our delta y. All right, so I plugged in all my numbers. I really didn't have to do any algebra there, but you're going to find the product of these two, and then you're actually going to subtract the product of these because it's negative 9.8 there, and you get 1.28 meters for your max height, so check for our max height. Now for the final overall velocity, this one is actually pretty easy for this type of problem, but I'll show you the method so that you know how to do it for any other type of problem. So as the projectile is coming back down, we know that it has a horizontal velocity of 8.66 meters per second. And then at the very end, we know it has a final velocity of negative 5 meters per second directed downwards. So what you would normally do is you would use the Pythagorean theorem to find this final resultant vector right here. And then this is your final velocity, which you'd call your final overall velocity or your resultant velocity. This final velocity is just strictly in the vertical direction, but it's in combination with this 8.66 right here. So what you would do is you would take 8.66 squared plus negative 5 squared, and then set that to your VF squared. That would be like the a squared plus b squared equals c squared sort of thing for Pythagorean theorem, and then square root both of these sides. Okay, I already know that it comes out to 10 meters per second because that was our original 10. But in other cases where it doesn't fall all the way back to the ground or falls a little bit extra, you might have a different vertical component. But either way, you're going to use the Pythagorean theorem, and then that would give you the final resultant velocity. This one is still going to be 30 degrees. With the initial launch, it was 30 degrees above the horizontal. This is 30 degrees below the horizontal. In this video, we're going to be looking for an unknown angle of an object launched at 10 meters per second that reaches a maximum height of 3 meters. Now, in order to solve this problem, basically all we need is one part of our initial triangle. So what I mean by that is if we take a look at our initial velocity right here, I'll go ahead and pull it off to the side. We have the hypotenuse, which is 10 meters per second, and we have some unknown angle theta. So if we either find the x component or the y component of the object's velocity, then we can go ahead and find the angle by using a little bit of trig. Now, considering we have 3 meters, that is in the vertical direction. So we're actually going to want to find this over here because we don't have much to work with in the horizontal direction. So normally we would split up an x and y column. It looks like we don't really need to do that for this particular one over here. So we have a delta y of 3 meters. We have an acceleration of negative 9.8 meters per second squared, as usual. And then we also have one additional number, which is the final velocity of 0, because as something rises, it has an instantaneous velocity of 0 meters per second in the vertical direction at its peak, although it does still have some horizontal velocity. So now with those three numbers, let's go ahead and pick one of our formulas. We're definitely not going to use this one because this is a constant velocity formula. It looks like we're going to have to use this formula right over here because that's the only one where we have VF, A, and delta Y to find an initial velocity. So let's go ahead and plug into that formula and see what we get.
Avant, tu voyais que de la merde. Maintenant, au moins, tu vois plus rien.
All right, so I plugged in my numbers. I found the product of these three, which is negative 58.8, added it to the other side, took the square root of both sides, and I got 7.66 meters per second for my VI. So remember, that's just the initial velocity in the vertical direction. So for this one over here, that's where my 7.66 meters per second would fit in. So now that we have two sides of our triangle, what we're going to want to do is use an inverse trig function, and we're going to the opposite end for the 7.66, and then we're using the hypotenuse, so that would be the inverse of sine. So if we take the inverse of 7.66 over 10, that leaves us with our unknown angle. That's going to round off to 50.0 degrees. So to sum things up, when you're solving for a problem like this, like I said, you want to find one of these pieces of your original triangle, either your horizontal or vertical component of your initial velocity. And because we're given a vertical value to work with, we're going to work in the vertical direction and use that delta y in combination with the acceleration due to gravity and that instantaneous velocity at the peak to plug in and get that 7.66 meters per second. From there, you'll end with some kind of inverse trig function to find that unknown theta. So I hope that was. In this video, I'm going to be talking about how to predict where a projectile will land with an elevated angled launch. So every projectile problem has some different variations which make it a little different and potentially a little bit more difficult. So I would consider this problem a little bit more difficult than an angled launch off the ground returning back to the ground. So the first thing we typically do is we usually draw out a triangle, and we have the projectile being launched at 3 meters per second at a 20-degree angle, and we have an x and y component of the velocity, which I'll call Vx and Vy. So I'm going to go ahead and get started finding those two components, and then I'm going to start placing variables into my two columns shortly after. Okay, so as usual, I use sine and cosine. I use the sine of 20 degrees, so I could use the opposite end along with the hypotenuse, my known velocity of 3 meters per second. And then when I did opposite over hypotenuse, I just basically multiply both sides by 3, which would basically be 3 times sine of 20 to get me my Vy, which I put over here as 1.02 meters per second. I did the same thing for the x component, except that I used cosine so that I could get the adjacent side of my triangle, and I got my Vx, which came out to 2.82 meters per second. That makes sense because 20 degrees is not that far from 0 degrees. It's definitely under 45, so more of it is aimed in the horizontal direction, causing this velocity to be a little higher. Okay, so why do we break it up into an X and Y column? So it is really important if you're working on any type of 2D projectile type problem to split up into an X and Y column, because each of the different axes has a different type of motion. There is no force in the horizontal direction once it's launched, so it's going to be moving at a constant velocity. Therefore, we can only use this formula over here to the left. And then on the right side, we do have gravity acting in the vertical direction. Therefore, it's going to be accelerated motion, and we will use these three accelerated formulas over to the right. So over here, I call this VI because that is my starting vertical velocity. This side, I just called it V because it's constant velocity, so there is no starting or ending velocity. And we always know acceleration is negative 9.8 meters per second squared. Okay, now normally if you're doing an angle launch to where it returns back to the same height at which you launched it at, you could say your initial is 1.02 and then your final is negative 1.02 once it reaches the ground. But it's going to hit that negative 1.02 around here, but then it's going to fall an additional 1.1 meters. So in this case, we can't use a VF of negative 1.02. But we do have an additional piece of information, this delta y over here, which we will call negative 1.1 meters, and then I'm going to go ahead and drop that into my y column over here. Okay, and I'm going to make sure I label that as negative 1.1 because it's displaced downwards in the negative direction from where it was launched. So actually, sorry, I kind of drew this off a little bit. It would be the height from which it was launched, so somewhere around here. Okay, so the launch height is negative 1.1 from the height of the actual launch all the way to ground level. Okay, so anytime we have three known values, we can basically solve for just about anything we need with any of these kinematic formulas. And what I'm looking for is my delta x. I eventually want the delta x on this side of my setup, but I am missing a t. I'm looking for my time, and it turns out time is the only connecting variable that can be used in either of the two columns because it does not have a direction. So I'm going to take a look at my formulas, and I see that this first formula has a t in it, and this second formula has a t in it. But the first one, I don't have my VF, so I can't use that. So I'm going to go ahead and set up all my values in this second formula and then solve for t. All right, so I found my T, and it's definitely a little bit different than an angled launch where it lands at the same height at which it was launched. So I ended up having this setup right here where I put in my delta y, my vi times a t plus 1/2, and then the a negative 9.8 times t squared. And I set it all equal to 0. So when you get to this point over here, there are a few different routes you can take. You could go ahead and graph this and then see where your graph intersects the x-axis and hits 0. And then you'll have one negative number and one positive number, and obviously your time would be the positive number. You could use a quadratic formula, or if you have a more advanced calculator, you can just plug this in and then use the solve function. Any of those three ways should get you the time of 0.59 seconds. And remember, that was the time that I wanted over here. So now, after I multiply both sides by 0.59, I'm going to get my final delta x, and my delta x comes out to 1.66 meters. Okay, so if I were to measure exactly how far that was from the table, I'd probably use something like a string with an weighted object from the bottom to see exactly where the edge of the table is, and then measure 166 centimeters out, or 1.66 meters out. Okay, so to sum things up, anytime you have some sort of angled launch, you definitely want to set up your triangle, take your main velocity as your hypotenuse, and then find your horizontal and vertical components. And being sure and careful that you drop them into the two different columns, you have your A equals negative 9.8 meters per second squared as the acceleration due to gravity from the Earth. And then the additional variable that was given in this problem would be the height, and you want to make sure that's a negative 1.1 because in this scenario it was displaced downwards at 1.1 meters. But if it's displaced in the upward direction, then you can go ahead and leave that positive. And then from there, once you run into this setup right here, you may have to use a quadratic or graph it to find your time. And then remember, time is the only variable that can be used in both columns, which worked out nicely for us so that we could find our delta x. And then now we know that the projectile lands at 1.66 meters from the edge of the table. In this video, I'm going to be talking about a projectile basketball problem. if you take a look at our diagram over here, we have a person shooting the basketball 40 degrees from the horizontal upward towards a 3-meter tall hoop 2 meters off the ground from 5 meters away from the basketball hoop. We're going to figure out a few things. The first thing we're going to solve for is the initial velocity, which is pretty difficult in this case because there's a lot of factors involved in this problem that aren't typically involved with the average projectile problem. So if you see over here, I have my original vector, which is my VI, my original initial velocity that I'm looking for. I broke it up into the two components, the horizontal component and the vertical component, which I called Vx and Vy. Now, this problem has a lot of unknowns. Typically, if you have the VI, you can find the components and then everything kind of comes together from there. But if you don't have the VI, the problem can be pretty difficult. So instead of putting Vx, we know a little bit of information about Vx. We know that Vx is eventually Vi times the cosine of 40, which I showed a little bit of the work here of how I got that. And then my Vy is Vi sine of 40. Same reason, by using a little bit of trig and then kind of rearranging it so that we have something in terms of Vi for the y component and something in terms of Vi for the x component. So what we're going to do is we're going to use a couple pieces of information to help us out, along with the two things that I wrote on the bottom over here. And we're going to use the formula delta y equals the initial velocity times time plus 1/2 a t squared. Now we're going to have to do a little bit of substitution here. So for our delta y, that is our change in our vertical displacement. So we starting at 2 meters and then we're going upwards to 3 meters. So the delta y is 1 meter because it's rising up 1 meter from its original position. Now for the VI, we don't have anything to represent that. So we want the VI in the y direction, in the vertical direction. So we're going to go ahead and grab this over here and substitute out the VI for VI sine of 40 degrees. So that's going to represent my VI. And then we don't know the t, so we're going to go ahead and put the t in there. And then plus 1/2. And we know our acceleration due to gravity in the vertical direction is always negative 9.8 meters per second squared. And we still don't know the time, so I'm going to go ahead and write t squared there. All right, so what we can do is we can go ahead and do a little bit of rearranging to solve for what we need. The first thing we're going to do is we are going to do a substitution for time because we have two unknowns, a VI and a t. So if we could solve for t in terms of VI, then VI will be our only unknown. So what I'm going to do is I'm going to use the constant velocity formula, delta x over t equals v. So in the horizontal direction, we can use a constant velocity formula because there are no forces acting in the horizontal direction once the ball is released. So the ball is going to be moving horizontally in a constant motion. So the delta x is going to be 5, and the t is our unknown, and the velocity in the x direction is right over here. So we're going to go ahead and change that velocity to a VI cosine of 40 degrees. So we can just go ahead and cross multiply those two, and then 5 over VI cosine of 40 degrees equals our t. So now we have something to substitute in for the t that's going to be in terms of VI, so which would leave us with one unknown, and then we could just do a little bit of algebra to solve for our VI. So I'm going to grab this t over here, and I'm going to sub in 5 over VI times cosine of 40 degrees. So let's go ahead and rewrite this whole entire expression here. All right, so what I did is I just dropped down my 1, I dropped down my VI sine of 40 degrees, I subbed in my 5 over VI cosine of 40 for t right over here. I simplified the 1 half times negative 9.8 to negative 4.9 just by multiplying the two. And then I have one more t, but it's squared, so I just squared all of the things that I wrote down over here. So 5 squared is 25. My VI, I squared it, and my cosine of 40 degrees, I squared it. Now, when you're taking a look at this setup right here, it looks pretty complicated because there's a lot of trig functions, there's some squared values. It's not quite as complex as it looks. As you see it now, there are a lot of trig functions, but remember, trig functions are just numbers, mostly numbers that we don't know off the top of our head, like sine of 40 degrees and cosine of 40 degrees. So what we can do is we can go ahead and cancel out this VI because it's VI divided by VI, and then sine of 40 times 5 divided by cosine of 40 leaves us with 4.2. For our second part, I'm just going to put a minus sign here because we have a negative here. We can do 4.9 times 25 and then divide that by cosine of 40 squared, which leaves us with 207.63. And the VI squared is still going to be on the bottom there because that's our unknown. So it simplified down quite a bit because a lot of what we had were just numerical values, but numerical values that we could simplify. So again, I took the sine of 40 times 5 divided by cosine of 40 degrees. It gave me a single value of 4.2. Over here, I took the 4.9 times 25 divided by cosine of 40 degrees squared. That left me with 207.63, drop the VI squared on the bottom. So if I go ahead and subtract the 4.2 from both sides, then it leaves me with negative 3.2 on the left side of the equal sign. And then on the right side of the equal sign, I still have my negative 207.63 divided by VI squared. So I can go ahead and cross multiply these two. And then since we have two negative numbers divided by one another, I'm going to get a positive number, which is good because I need to square root it, and I can't square root a negative number. So I'm going to square root my VI squared and square root this value over here. And then my value for VI comes out to 8.05 meters per second. Okay, so we had a lot of substitution going on and a lot of just busy work towards the end, doing a little bit of algebra, simplifying some expressions, and then ending up with a final velocity of 8.05 meters per second. So I'm going to go ahead and add that to my original picture. And then for the second part of my problem, I'm going to solve for a few more values. I'm going to solve for the time. I'm going to solve for the final velocity that the basketball goes through the hoop along with the angle. So the first thing I'm going to do is solve for time. And what I did was I erased some of my work just to give myself a little bit more space. But I did notice that I had a formula that I kind of set up earlier that would give me time. So I'm just going to go ahead and use that. And I have 5 over VI, which I know is 8.05 meters per second now, times cosine of 40 degrees. And then my time comes out to 0.81 seconds. Now we're going to find that final velocity going through the hoop. Now it's going to go through at an angle. So what we're going to do is we're going to find the horizontal component and the vertical component. and then combine those two using Pythagorean theorem, and then we'll be able to solve for our final velocity going through the hoop. So for our Vx, our horizontal component, that one's going to be pretty simple because, as I said before, the horizontal motion is constant because there are no forces acting in the horizontal direction once the ball is released. So we can go ahead and say that the velocity is, and I'll just take this original formula over here, is delta x over t, and that gives me 6.17 meters per second. Now for the y component, what I can do is I want to use an accelerated motion formula because the motion moving up and down is accelerating because of gravity acting in the vertical direction. So if I want a final velocity, I can do vi plus a times t. And I'm looking for my vf, so I'm going to go ahead and write vf. My vi in the vertical direction is 8.05, which is my initial velocity, but times the sine of 40 degrees, okay, as I set up over here. So that's my VI, and then plus, and then my acceleration, as usual, is negative 9.8 meters per second squared for something that's in free fall motion, times time, which is 0.81 seconds. All right, so what I can do from there is take 8.05 times the sine of 40 and then add that to negative 9.8 times 0.81, and then I get a final velocity of negative 2.77 meters per second. Now that velocity is going to be fairly small because the ball is going to go up to its peak, and then from its peak it's only going to come down somewhat until it hits the hoop, so it's not going to come all the way back down towards the ground. So I have the two pieces that I wanted, so I can go ahead and put those together now. So now we have all the information we need to find our final velocity. Our final velocity is our angled component, which is our hypotenuse of our triangle, and our horizontal component is this 6.17. And then our vertical component is this one over here, the one that is going downwards, 2.77 meters per second. Okay, so what we can do is go ahead and use the Pythagorean theorem, and the Pythagorean theorem will give us the hypotenuse, which is the final velocity. So after using the Pythagorean theorem, I took 6.17 squared plus 2.77 squared, or negative 2.77 squared, which is the same number, square root of both sides, and then I got a final velocity of 6.76 meters per second. So the last thing we're going to do is we're going to solve for the angle. And the angle below the horizontal is going to give us our final theta value. So we can use a bunch of different values. The one I'm going to use is the inverse tangent function, but it doesn't really matter which one you want to use. So if I go opposite of my angle, I get negative 2.77, and then over the adjacent, my adjacent side is 6.17. That gives me an angle of negative 24.18 degrees. So we can pretty much just call that 24.18 degrees below the horizontal, and that gives us our angle at which the ball is entering through the hoop. So as I said before, you could have used an inverse sine function or an inverse cosine function because we have all the sides of a triangle, so using the inverse tangent was just a random choice of mine. Either way, you're still going to get the same angle as long as you place the numbers in the right spot. So I hope that was helpful in helping you set up and solve for the VI, the T, the final velocity, and the angle. Thank you for watching and listening.